Hi everyone. I would like to introduce myself first. My name is Sandi Prayogo and I come from the NTUSD. And I would like to present to you my research on the active learning based Kriging on for the reliability analysis. First, we have the Kriging predictor. Maybe I can uh, show a few slides that introduce the Kriging predictor. So I will not be explaining how the Kriging is calculated, but rather the function of the Kriging model. The Kriging model, or the GPR, which is Gaussian process regression, was initially developed for the geostatistics. So it is used to calculate the mining operation. So we have the the coordinates of a mine. So we have the x and the y and the z of a point for the mining, and it will interpolates the area for it. So the Kriging model calculates the response by combining the polynomial regression model, which is like the linear regression model, with a zero mean Gaussian process, which I will briefly mention. So basically, I will oversimplify this. The Kriging model interpolates the values which is considered the surrounding known values. So the nearest will be calculated as an input, and the Gaussian process will show the confidence of the prediction. So if you have less known values near the point that you are predicting, it will have a high uncertainty, rather than if it is close, then it is very high. It is very sure that it's true. So the toolbox of Kriging is readily available, such as DACE. It is available in MATLAB, but I'm not sure in Python. So this is an example of the Kriging prediction. So the black dots here, are the known values. So this is an example of a valley. So we have the XYZ coordinates of a valley, and the Kriging predictor will interpolate the unknown values. And this is what I mean by the confidence of the prediction. It will also give you the mean square error of the prediction. The mean square error is synonymous to the variance of the prediction, or the standard deviation of the prediction. So this will be the mu, and will be the sigma. So at the prediction, the sigma will be equal to 0. So it only has one value. But if it is not is unknown, depending on the distance to the nearest known value, it could be a very high variance. So the Kriging predictor is really popular because it gives us these two things: the prediction value and the confidence of the prediction. If it's far away, then the confidence will be very low and the uncertainty will be high. Next, we have, this is also an example of the 2D, the 2D prediction. So we have this is the known value, the red one here. And we have the mu, which is the Kriging prediction, and the sigma, which is the mean square error that we show in the last page. So the sigma will show the certainty or the uncertainty of the prediction. So in here, it is very uncertain because it is far away from the known points, but closer to the known points, it will get the higher and higher confidence, until if it is predicting the known points, the sigma will be 0, the mean square error will be 0. Okay, so for the reliability analysis that uses Kriging, there are many. I think it started very early, but the AKMCS is the pioneer, the one that is popularized the use of the Kriging at at the reliability analysis. So it will use the active learning. So this stands for active learning Kriging. Adaptive Kriging also is okay. So the first step is generating the candidate samples for the Kriging, which is the Monte Carlo simulation. So this will be the Monte Carlo simulation, and the blue line will be the limit state function. Step 2 will be generating the initial samples. So like last week, we have to make a design of experiments, which is the training samples as the candidate, and train the Kriging model with this input and do the active learning function. Because what do I mean with the active learning, which is we iteratively find the best sample to improve our model. So what is the best sample in this case? So we have the best sample would be the one that is most informative samples. So the one that carries the most information that we can add to the model. So in reliability analysis, we only focuses on the limit state function. The samples that are far away from the limit state function, we don't care. For the last example, this is the Monte Carlo simulation range, right? So we don't care about this sample at all because it is very far from the limit state function. So the prediction in here, if it is changing by 1000 minus 1000, it doesn't matter because it is far away from the limit state function. Another thing that we must consider is that we want the point that is in the area with few training samples. So for example, we have a lot of training samples here, right? This is also the limit state function, and this is also the limit state function, but this area is unpopulated with the training samples, so we have to prioritize this area first rather than continuing to improve this area, because there are few to none existing training sample near here. So with these two function, generally the active learning function will generally pick these two criteria. So the AKMCS use the U learning function, which combine the mu, which is the prediction value, and the sigma, which is the confidence of the prediction. If it's close to 0, the mu will be small, and if the sigma is high, so we want to pick the mu that is equal to 0 and the sigma that is high. So this will lead to a small mu. So we choose the U function that is have the smallest possible value within the candidate samples, and we just put the new samples and retrain the Kriging with the new points and repeat the active learning. So this will repeat again and again and again until all of them passes a certain threshold. So in this case, the U function must be larger than 2. If it's all larger than 2, then it is considered to be the limited function is considered to be fair defined. So what if the Monte Carlo sample is not enough? For example, you have the limit state function that is very far from the center, so it needs like 10 to the power of 7 samples to calculate. We just, after the step 4, we just add more samples to the Monte Carlo simulation by checking the COV. If the COV is fulfilled, for example, we need the COV is less than 1%. We just adding the Monte Carlo simulation and come back to the active learning, and we do this over and over again until the COV is less than 1%. So this is the example of the Monte Carlo the AKMCS. It will pick the samples that is close to the limited function, while also picking the samples that are far away from each other as possible. As you can see, at the start, the limit set function is not good, but by adding more samples, the limit set function is good enough. So we do not care about this function in here and here because there are no Monte Carlo samples there. Even if it is not correct, it doesn't matter because it doesn't calculate, it doesn't affect the probability of failure that we are calculating. So in this case, the AKMCS requires about 40 samples, while the Monte Carlo simulation only have to use the 90,000 samples to get the same amount of COV, the coefficient of variation. This is the flow chart of the AKMCS if you are interested in reading. And then next we have the AKMCS. So the AKMCS uses the Kriging to predict the limited function with very few evaluation. So it's almost 2000 times more efficient. In this paper, it is said that the Kriging evaluation is free because it's very fast. In my computer, it's 100,000 points, only takes 0.17 seconds. So if you are using the finite element method, which uses maybe 1 seconds, 1 seconds of calculating and doing the Monte Carlo simulation, you will take maybe for 1000 points you will take 1000 seconds in here, while the Kriging only takes for 100,000 points, it only takes less than a second. But it is not free because it is calculating something. So if the Monte Carlo simulation takes like 10 to the power of 7 samples, the efficiency will decreases a lot because it is have the cost of accessing the memories, which is the memory cost, and the computing cost, which is the flops, the floating point of operation. And if it is very high, it will incur memory problems when it tries to calculate all the distances, because the Kriging will calculate the distance between the points, and if it's very big, then it will require the number of samples to the power of 2, which is may need high random array memory. In conclusion, it still has a weakness in low probability problems. So what did the researcher do? They implement other variants of Monte Carlo simulation because the AKMCS is fairly simple and uses the Monte Carlo simulation. So we just change the Monte Carlo simulation to other things such as the importance sampling, the line sampling, the subset simulation, the radial-based importance sampling, or the directional sampling. So the other researchers are currently doing this. So what is my research? So my research is trying to improve the work that are published by Kim and Song, which is the PAK-BN. So they are doing the Kriging on the hyperbole. So the PAK uses the hyperbole region and using the importance sampling. So it's like an importance sampling, but using the hyperbole region. Hyperbole is the, because as you can see at Monte Carlo simulation, the samples will generally look like a circle. So they use that effect and using a ball to represent the region of interest in here. So my research tries to improve these weaknesses. So this is my research. As you can see in here, it started here similarly to, but we use the importance sampling. So we don't use a Monte Carlo simulation. Rather, we use a uniform distribution, which is in a hyperbole region. Because it's 2D, it's a circle. And it improves like that. So we have a better learning function which is emphasizing the inner radius because it has the highest amount of power in regarding to the probability of failure, and it is better in complex and high dimension problem, but maybe not in the simple problem, because simple problem, even if the learning function is not good, it still gets a decent result. So it may not be more efficient in there. It is important sampling, which is needing 10 to the power of 4 to 5 samples, which is good at low probability of failure. We have the hyperbole expansion, which I will explain later. It doesn't use rejection sampling. We filter the samples that are already well defined to avoid unnecessary Kriging evaluation, and adding an alternative error-based stopping condition. So if the limit state is noisy, for example, it's like this here. If the probability of failure is already converged, we don't need to do this like this, like this, like this, like this, like this. Maybe just a general definition is okay, because the probability of failure doesn't really change that much. So we implement an error-based convergence stopping condition. So we have the probability of failure here. So the important samplings requires the original PDF and the proposal PDF. The proposal PDF will be the hyperbole sampling, which is defined by 1 over the volume of the hyperbole, which is calculated in here using the hyperbole formula, which is the pi to the power of the dimension divided by 2, and using the gamma function to calculate the constants of the volume in here. So what is wrong with rejection sampling? To generate the hyperbole distribution, the hyperbole region, they use a rejection sampling. So it's just generating the uniform distribution in a square here by 6 n minus 6 and 6 by n minus 6, and throwing out the samples that have the radius larger than 6 is removed in here. So we have an efficiency of 78% because we remove these corners, but the efficiency will be worse and worse as the dimensional increases. So it is very, very inefficient in high dimensional. At 10 dimensional problem, we have an acceptance ratio of 0.2%. So it's gone from 78% to 0.2%, which is very, very inefficient. Another problem with the rejection sampling, if we have two different radius, because we start with a smaller radius and expand to a larger one, we have a different density. In the inner density will be more dense in here, and the added density will be not as dense as the center. So we have two different density, while the the volume, that is the h, which is given by the Kim and Song, only provide one density, 1 divided by v, the volume. So what I did is we embrace the multi-layer, which is each layer may have different density, and calculates the density of each layer. So the calculation is simple, which is we enforce the PDF rule that the integral of all PDF should be 1 in here. So the volume times the h, and we combine it for all layer should be 1, and the ratio of each layer should be according to the volume and the number of samples that is within this layer. Like this layer have the higher volume than this layer, and the numbers of sample here and here, if it is the same, then this layer will be more loose, and this layer will have more dense sample. So we put these two together, and using the matrix operation, you can get the PDF of each layer. So we have H1, H2, and H3. So for the learning function, maybe I don't really delve deep. If you want to read the learning function that I use, you can read the Zhang et al. At 2019. I think the paper also have REIF as the title. Basically, they use a folded normal PDF, which is the normal distribution, but they have only take the positive values, and also added the PDF, so it prioritizes values that are closest to the middle in here. So we also do some research that we also find that by expanding more than 1 by 1, so in PAKBN, they only expand 1 by 1 by 0.2, and by expanding more than 1 by 1, maybe you can expand up to 5 times here. You can get a better placement in here, which is saving samples that may be used at a later date. For example, here they use 2 samples in here, while in here they only need 1 samples. It is enough. In here it is closer to the limit state function, and in here we put 1 more sample here, and we can get a better limit state function. It may save 1 or 2 samples in the 5 in these 5 next samples, and 2 samples efficiency is very good. For example, for this problem, the AKMCS only have 40 samples, right? It's equal to about 5% improvement in here just by doing this. Okay, and this is the filtering well-defined areas. For example, in this so the left figures shows that this is what the algorithm says, and this is what actually happens with the probability of failure. So because the Kriging functions, actually we calculate the limit state function using the Kriging function again and again, but actually we don't need to do that, because in here, because the limit state function is up here, we actually can just throw away these samples in here. So I develop a way to filter out the samples that are already well defined, so there are no need to add them again to the calculation, which can save almost 90% of the Kriging computation. So we can save a lot of Kriging computation, which is considered free but actually not. And I think that's uh, all of my presentation. If you have any question, maybe I can answer them if we come back to a normal class. Thank you very much.